Today we are going to see maximum principle of harmonic function. Suppose U is harmonic in the open connected domain D. Okay. So, for this part of our discussion we would consistently use this notation. Capital D would be used to denote open connected domain of D dimensional Euclidean space. If U, the harmonic function which is defined on open D, if U achieves its supremum on over D, okay, at some point in D, then U is identically constant. Okay. So, this is the statement of maximum principle. We are going to see the proof of this fact. Basically, okay, before going to the proof, let us try to understand what does it imply. It implies that only constant harmonic function has the property that maximum is value is achieved in the domain of D. Okay. But other than constant function, why constant function is harmonic? Because harmonic functions are the functions whose second order derivative is 0, that Laplacian of U is 0. Okay. In one dimension case it is just second order derivative, in higher order case it is trace of the second order derivative. Correct. So, constant function is of course harmonic in that sense because its derivative is 0. However, if you have a trivial harmonic function, then it actually goes up and down, etc., and then the maximum of U over this open domain, that value would be something strictly more than all the values you have taken inside the domain. Okay. So, if you extend this function over the domain, okay, over the boundary, then possibly you would see the maximum values achieved in the on the boundary, if you can do that. Okay. So, the proof starts here. This proof has many steps. Okay, and it's not long proof, just one page long. So, let M be the maximum of U, okay, the supremum of U. We cannot say maximum because it may not be realized. Supremum over open domain D of the function U. We also denote D subscript M. D subscript M is a subset of the open domain D. It is basically level set. Okay, the level set. It is not a lower level set. It is exactly the contour actually, that when Ux is equal to M. This is a set of points on D where you take the value capital M. Okay. If U does not take the maximum value at any point in the domain, then this should be basically empty set. So, our goal is to show that this is empty set. Okay. So, that is the statement of the theorem, that it should be empty set. Okay. So, for that we prove by contradiction. What we do is that it's not actually by contradiction, it is just saying that if we consider that this set is non-empty, then we should obtain that Dm is equal to D itself. We should yes, it should be capital M. Okay. This capital M should appear on the subscript. So, our plan of proof is that if this set is non-empty, we should obtain that this set is exactly the whole set. What does it mean? That means that the function is constant. Every point is maximum, that means the function is not changing its constant function. Okay. Or in other words, except constant function, for any other case this Dm would be empty, okay, contrapositively. So, we proceed in the following manner. We assume that Dm is non-empty. So, what does it mean? That means there exists a point A in this set Dm, okay, and then consider, since A is also in a subset of capital D, point in capital D, and capital D is an open domain. So, I can consider a ball of radius r around this point such that the closure of the ball is still contained in the domain D. Okay, we do that. So, consider a sufficiently small r positive such that the closure of the ball of radius r around the point A is inside the domain D. Then due to mean value property, because mean value property we can use now, as u is a harmonic function, we have already shown that harmonic function has mean value property. So, here capital M is equal to u of a, I mean basically because a is in dm. So, we have this. Now, using mean value property we are writing this equality, u of a is equal to the volume of this ball, okay. Vr is nothing but the volume of Vr, and then integration of u over this ball, okay, over this ball a plus Br, okay. So, how do you do that? We write u of a plus x, x is running over Br, is synonymous, okay. So, we get this. Now, u of a plus x, okay, these values, okay, can never be more than capital M, because a plus x is always in D, okay, because B, this is inside the D, okay. So, maximum of u on D is M. So, u of a plus x cannot be more than M. However, this average is M. That can only be achieved if u is equal to M, okay, almost everywhere. However, u is continuous because u is harmonic, okay, is continuous. So, almost everywhere equal to M is basically saying that it is exactly equals to M everywhere inside this ball, okay, u of a plus x, where x is here. That means u is capital M on this ball of radius r around the point A. So, this implies that this ball is subset of Dm, because Dm is basically the set where u takes value M, okay. So, therefore, this open ball is inside Dm. So, what was the consequence? We have picked up one point A from Dm, and now we have obtained that A is an interior point of Dm, okay, because A plus some ball, okay, that is in Dm. So, that proves that Dm is open. However, Dm can also be rewritten in another way, that u inverse of capital M. So, here this is the definition, correct? U inverse of ux is equal to M, okay, for all those x in D. That means this is intersection of D and u inverse of M. So, Dm can also be written as D intersection u inverse of M. So, if you look at the subspace topology of D, so there Dm is a closed subset, because u is a continuous function, continuous. So, inverse image of a closed set under continuous function is closed. So, we are going to get Dm is closed in D. So, we have obtained both. We have obtained Dm is open and also Dm is closed, okay, open in D and closed in D, okay, and D is also connected. So, only possibility is that Dm must be either D or empty, but we have started with non-empty. So, it should be D. So, Dm is D. So, that is the proof, okay. So, this is whatever I just told, it is written here as D is connected, D is non-empty, and therefore, Dm is D. So, the result is that, let me summarize then, that mean value property implies harmonic function and C infinity, so which we have not proved here, but I am just giving a reference, page number 242 from Karadzic and Shreve book, which is our reference book. So, this part, and the other part, that harmonic function is having mean value property, okay, and so this is actually not the consequence of this particular theorem, but about our discussion before closing this part. And harmonic function is having mean value property, and mean value property implies harmonicity and also C infinity, infinitely differentiability, okay.